Hello, my name is Martin Zubeldia. I'm a postdoc at Georgia Tech, and today I'm going to be talking about learning traffic correlations in multi-class queuing systems by sampling workloads, which is a joint work with Michel Mandjes from the University of Amsterdam. So our inspiration for this was a routing in the backbone of the internet. So here's an example from the OVH Europe network. There's a few servers connected by fiber optics there. And the properties in this network is that the traffic is highly aggregated. We have a lot of users traffic being aggregated in this network. And also because of this, the routing is mostly static because there's just too many packets and flows to do any sort of packet level, flow level routing. So a stylized model of this type of networks can be seen as static load balancing. When on one hand, we had case servers, possibly with different rates, and each one with its own queue to store works that needs to be done. On the other hand, we have different classes of traffic that arrive as some arrival process, m-dimensional in this case. And for each type of traffic, we have a router that tries to split the traffic among the different servers. Now, there can be compatibility constraints between the types of traffic and the servers, but in this talk, we're going to assume that any type of traffic can be served by any server. Now, what else are we going to assume? Well, kind of using a central limit theorem approximation, we're going to assume that the arrival process is some m-dimensional Gaussian process with some known rate lambda and unknown covariance matrix sigma. And these two actually completely determine the Gaussian process. And we're going to assume that the routing is a static deterministic split according to some routing matrix R. So each router just decides to split the arrival process among all the servers deterministically. And our objective here is to learn what's a routing matrix that minimizes the maximum of the probability that these queues go above certain threshold. This can be, for example, for quality assurances purposes, we cannot go above certain threshold because there's going to be too much delay. So we want to learn the best routing matrix, and I say learn because the covariance matrix of the arrival process is unknown. So we kind of have an additional assumptions on the arrival process. Because the traffic is highly aggregated, we assume that we're in what is so-called the many sources regime, where the arrival process is actually the superposition of a very large number, here little n, ID processes. And for simplicity, for the purpose of the talk, we're going to assume that they're not just any Gaussian process, but multivariate fractional variant motions, which are the ones that the covariance matrix has a very particular shape. This includes the Brownian motion. And what's most important here, perhaps, is that the covariance is of order 1/n. So the more sources you have, the less covariance that you have. So how do we actually find the optimal routing matrix? Well, we propose the following. So we start with some initial routing matrix R0. Then we observe the queue length and estimate the steady state distribution under that routing matrix. And then the key here is that we use an inversion procedure to get the covariance matrix. And this is kind of the key of this algorithm. And then once we get the covariance matrix, we use some large deviation approximations to get the probability of going above the threshold for any routing matrix. And we optimize offline to get the best routing matrix. And this has two important advantages. One is that the queue lengths are much easier to estimate than to directly trying to estimate the covariance by looking at the arrival processes. Also, there has very fast convergence because we don't need to iterate on different routing matrices. We just find it on one go. So in this talk, I'm going to focus on this inversion procedure. So the first one, it's actually inspired by a paper by Mandjes and Van de Ment in 2009. who proposed sort of this inversion, but without proving it that it actually works. It was mostly a systems paper with a lot of simulations backing it up. I recommend you go see it if you want to see more simulations of these sort of things. But the idea is that the workflow in the systems goes from the arrival processes, AN, through routing, you get input processes, which are linear combinations of the arrivals, and then queuing, you get the distribution. And then the inversion would be, okay, to get the distribution of the queue length and somehow get the variance of the input process. And we're going to try to get this inversion based on a large deviation principle for the probability of the queue being above certain threshold, and that this is an optimization problem of a function that depends on the service rate of that particular server, the total arrival rate, and on the variance of the input process. So that's why we're trying to invert this. So we try to do that. We get an estimator of the variance, which is again an optimization problem, but now it depends on the empirical distribution of the queue length after big N samples. And we actually show that if you take the number of samples going to infinity and then the number of superimposed sources to go to infinity, so this is the first limit for the accuracy of our empirical distribution, and the second one for the accuracy of our large deviation approximation, then the estimator converges to the true variance almost surely. So using this estimator, we try to find all the distinct covariances of the arrival processes. And for each one of the KQs, we actually obtain a linear equation on these covariances. But we only have K. So if we can get enough equations by repeating this inversion procedure for different routing matrices, so we can get enough linearly independent equations. So we can need to pick these routing matrices cleverly enough. Now we can find the covariance of the arrival processes, but we need to repeat this a few times. The thing is, we only use the marginal queue lengths. Can we use the joint queue lengths to actually get more equations directly, so we can do it in one go? And the answer is yes, and that's where our second inversion procedure comes in. Here we use pairwise joint queue lengths. So from the arrival processes, through routing, you get a pair of input processes to two queues, and through queuing, the pairwise joint queue length distribution. And we want to go from the pairwise joint queue length distribution to the covariance of the input processes. And now again, based on some large deviations approximation, but now looking at the linear combination of queues instead of just one queue. And it will depend on the variance of the sum of the input processes. Again, we define a variance estimator that's at the infimum of some function that depends on the empirical distribution of these linear combinations. And we show that at least in some cases, when the input processes are short range dependent, which includes the Brownian motion, and the input processes are non-natively correlated, then we actually have the convergence of our estimator to the correct covariance, almost surely. And now in these cases, we can actually find the covariances of the arrival processes in one go. So for each of the queue lengths, using the first inversion procedure, we could obtain a set of linear equations. Now, for each one of the different pairs, we get another linear equation. And if the number of types of work is less than or equal to a number of queues, these are enough for a single routing matrix to get the whole covariance matrix of the arrival process. Now, this is not always possible. There's actually a fundamental limitation. And this is that if the input process is actually long range dependent, and the input processes, the ith and jth queues are negatively correlated, then the covariance of the input process can never be recovered from a large deviation behavior of the linear combination of queues. So there's an inherent loss of information here. And this was interesting. Like, why do we have this limitation? And of course, there's the proof, but I think that a better intuition is to think about queues as reflective processes. Now, it's well known in queuing literature that the queue processes, not the distribution, but the whole stochastic processes, are the reflection at zero of what's called the free workload process, which is just the input process minus the total processing power of the servers. And the thing is, in this case, because of negative correlation, when one of the input processes grows faster than usual, the other one is more likely to grow slower than usual. So when one of the queue increases, the other one is more likely to decrease, but it's reflected at zero. So actually the magnitude of the correlation, so how much it's going to decrease, is actually lost in the reflection at zero. So that's where you kind of lose information about the magnitude of the correlation. So to conclude, the input variance actually can always be recovered from the queue lengths, and the arrivals covariances can be recovered with a few iterations at most. In some cases, the arrivals covariances can be recovered directly with one iteration. And in some other cases, actually, the inputs covariances cannot be recovered using these large deviations approximations. So there's a fundamental limitation here. And the nice thing about this is that this whole procedure can be extended to multipath routing in acyclic networks of queues. We just need much more involved large deviation results that we actually have. So it can be done. So that's it. Thank you.